All right, so we're going to talk today about this new standard that SMPTE is about to imminently publish. I don't think it's actually been published and available for purchase yet, but if it isn't, it will be very soon on the immersive audio bitstream. So first, a little bit of overview. I'll start with background and terms so we can all get on the same page. And for those of you that attended a presentation about a week ago on immersive audio by Brian Bessa, I must admit I just viewed that, and you'll get a little bit of repetition in this presentation, and I apologize for that, but perhaps in this case repetition is good. It will be quite different in the middle. We'll look at the high-level bitstream frame and element structure so you understand how the bitstream is composed and what goes in there. We'll look at the hierarchy of bitstream frame elements so you understand the logical nature of how the bitstream is composed. We'll take a look at the audio object coordinate system. It is a little different than other coordinate systems that you may have seen. Let's see, we'll talk a little bit about features of the bitstream such as extensibility, backward compatibility, and efficiency mechanisms. We'll look at specific examples of bitstream usage just so you can sort of pull all the concepts together and see how it would work in specific examples. And we'll look at how the bitstream is actually packaged for distribution in cinema and IMF applications. Okay, so first I wanted to, for background, I wanted to talk a little about the work of SMPTE 25 CSS Technical Committee, which was the technical committee that authored these groups, or excuse me, this group of documents. In this case, CSS stands for Cinema Sound Systems, and so this is a group that took on basically the task of trying to create a standard to allow interchange of immersive audio files for cinema distribution. And the first task we took on was to standardize immersive audio metadata. That was, at the time, that was, we were trying to start with a blank sheet of paper, and that was the easiest thing for the various parties to agree upon, was what audio metadata really was essential to carry for delivery to playback. So that's ST2098-1. ST2098-2, of course, is the standard we're going to discuss today. There's also a document on immersive audio rendering. This is an engineering guideline, which is why it has the preface EG. An engineering guideline is not a standard. It is a recommendation and guidance for people that want to implement something. And in this case, it's documentation of rendering expectations. So it basically takes the metadata items defined in 2098-1 and basically outlines what should people expect a renderer to do with those. There's also a recommended practice, which basically takes the expectations defined in 2098-3 and says how would you use those to use test material and set up a playback environment for testing of renderers for interoperability. And finally, if I can get this clicker to work, this is the only one in the suite that has been published so far. It's a listing of D-Cinema immersive audio channels and sound field groups. This allowed us to standardize the channels and that are carried in the bitstream since they had no normative definition up to that point. I wanted to point out that the scope of ST2098-2 is pretty generic. It just, in fact, in the scope itself, it says it defines a coded representation, parentheses, bitstream of an audio program. But I wanted to point out that digital cinema is the intended application, and that affected the choice of supported channels, the choice of supported speaker configurations, and the assumptions regarding playback environment. Now, that doesn't mean it's set in stone, but this was the task we were faced with, was really how do we get immersive audio in an interoperable manner to cinemas. But you'll see in the later in the presentation that this can be adapted to other applications. Some more background in terms. I thought it'd be worth talking about what is immersive sound, and particularly what's the difference between that and surround sound, which some of you might be familiar with. It's actually fairly simple from ST2098-5. Immersive sound includes sound that emanates from sources at or beyond the base layer. What's the base layer? That refers to the nominally horizontal plane of loudspeakers used in 5.1 and 7.1 configurations, here called sound field configurations, which, getting into the definition of that, that's an arrangement of speakers intended to reproduce a specific sound field. So basically, surround sound uses the base layer, and then immersive sound builds upon that by using typically height layer speakers. And also note that immersive sound does not have to use audio objects. In other words, if you can have channel-based immersive sound. And speaking of channels, here's the SMPTE definition of an audio channel. It's a distinct collection of sequenced audio samples that are intended to delivery to a single loudspeaker array, or other reproduction device. I like to think of channels as audio samples that are routed. In other words, it's tagged with a label saying, when you play me back, I'm expected to go here. And all the samples in that channel go to the same location. An audio object, by contrast, is a segment of audio essence with associated metadata describing positional and other properties which may vary with time. And so I like to think of audio objects as channels as being routed, objects being rendered. So it's up to a rendering device to figure out what speakers or groups of speakers to send it to. Bed is a term we use in the immersive audio bitstream. It's a sound field group, which is a group of channels, such as 5.1, 7.1, or 9.1, that serves as the foundation of the immersive soundtrack mix. So this was something that in the early days of immersive sound, at least at Dolby, we got feedback that sound mixers really wanted to start with something that was stable, that they were used to, and then they could add objects on top of that. Target environment is a specific set of conditions that is present in a playback environment. You'll see how that's applied later to conditional objects. Okay, so before we go into Bitstream Structure, I thought I'd pause here and see if we have any questions.
There are no questions at this time.
Okay, very good. Let's dive into the Bitstream Structure then. These next few diagrams are high-level simplified diagrams just to really show how the bytes are stacked together in a bit stream. The top diagram here shows the bit stream, which is a sequence of bitstream frames. A bitstream frame is composed of a preamble and a IAFrame. The IAFrame stands, of course, for immersive audio frame. The preamble is really a legacy element left over from Dolby's implementation of immersive audio, which was the basis for the SMPTE standard. And it really has no use in the standard other than the fact that it had to be allowed for in order to make existing content compatible with the standard. So it's really just sort of left undefined, other than the fact that if it's present, it should be empty, and the standard even allows it not to be present. So what we're really going to be talking about is the immersive audio frame, which is where all of the metadata and essence that defines the immersive audio program are contained. And typically what you'll find in a frame is one or more beds, one or more objects, and then audio data elements. And note, you'll see this later, that the audio data is carried separately from the metadata that describes a bed or describes an object. And I've thrown in another element here just to show that there's more elements than object and beds, and we'll get into those later. I also wanted to show that in some cases, elements can be composed of, or excuse me, the metadata in an element can be subdivided in time to allow the metadata to change over the course of a frame. And this is for things that might change quickly, such as an object position. It can change several times a frame, and that's what the subblocks are for. So now we'll take a look from a logical point of view. The bitstream defines at its highest level an immersive audio element, and all elements in the bitstream follow this basic pattern, or you could say derived from this model. They have an element ID and a size, and then contents. The element ID identifies the element and its syntax, and decoders may skip unrecognized IDs. So element IDs must be unique. Element size is how you actually skip. It basically is a byte count, so you know where the element ends. The combination of these two items allows extensibility. So as I mentioned, the standard is based on what was used for Dolby Atmos, and in order to allow content that existed to be compatible, we had to follow some rules, and one of those rules was not to change the existing elements, but if we put new elements in, they were optional, and then the combination of these two, element ID and size, basically works like KLB coding, if you're familiar with that, to allow skipping of an unknown element. And as mentioned, all bitstream elements are based on that structure. So now let's look at the highest level bitstream element, which is an immersive audio frame. So you can see it has an element ID, element size, has additional parameters such as bit depth, frame rate, max rendered, which I'll discuss more in detail later, and a sub-element count. And that's the thing I wanted to focus on here, is that the immersive audio frame contains all those other elements that you saw me mention a minute ago. And the sub-element count is what determines how many sub-elements there are and allows the parser to find all of them. I think it's important to point out that the bitstream's specification specifies a single immersive audio frame. That's what it really defines, and it does not constrain bitstream content with regards to adjacent frames. Each IAFrame is independently decodable, so you don't have to refer to any frames prior to or subsequent to the frame you're looking at. And applications can and do constrain bitstreams to contain IAFrames with consistent parameters over the length of the bitstream. For instance, you would want, for instance, bit depth and frame rate to remain the same over a bitstream, otherwise it makes decoding difficult. All right, I'll take a look at some other elements. As mentioned earlier, there's beds and objects, so let's take a look at a bed. As mentioned, this is a group of channels. Bed definition is the actual name of this element in the bitstream spec. It has an element ID, element size, and then this new parameter called meta ID. Meta ID is used to identify a particular element within a group of element IDs. For instance, within a group of objects, meta ID identifies that specific object, or if there are multiple beds in the bitstream, which is supported, the meta ID allows you to separate, identify one bed versus another. There's a conditional bed parameter, which identifies the element as being conditional or not. We'll talk about that more later. A use case, which is associated with the condition. The channel count, which I'll discuss now, basically tells you how many channels are in this particular bed element. And there's going to be one of these metadata structures for each channel. And so for each channel, there's an ID, which basically is a routing destination, an audio data ID, which points to the essence element that carries the actual essence associated with that channel. There's a channel gain parameter and a channel decore parameter, which stands for a decorrelation effect. So anyway, as mentioned, there'd be one of these for each channel and one essence element for each channel. In this case, I've shown the audio data DLC element. There are two elements supported by the Bitstream: audio data DLC, audio data PCM. You can probably guess what PCM is. Audio data DLC is losslessly coded audio data. And basically it's very simple, just the ID, the element size, and then the audio data ID, which is used to link this bit of essence to this channel in this case, followed by coded audio data. I should point out that for cinema applications, the lossless coded is the only audio essence that's supported. There's the ability to include audio description text, which is basically a free text field, and a sub-element count. As mentioned before, this is part of the basic element definition, and bed structures can contain other sub-elements, which we'll look at later. So to review, the bed forms the basis of the mix. Channel ID determines routing destination. I should point out channel count and channel ID are not constrained by the spec. You could have one channel in there, you could have two channels. You can't have more than one of any given channel ID, but there's no constraint on which channel IDs make up a bed. And each channel references an audio data element. Okay, moving on to objects. They're a little bit more complicated. These three parameters at the beginning you've seen before, along with audio data ID. Unlike beds, there's only one audio essence element associated with any given object. The direct relationship between the mono essence and the object. It can be conditional, so there's a parameter for that. And then we'll take a bit more look at this. This is what's called the Paninfo in the spec. This basically is where all the rendering metadata is carried. It can include gain, object position, object snap, which we'll talk about a little bit later, zone control, object spread, and object decorrelation. So this is basically all the rendering information for this object, and it's carried on a per block basis. Again, you can have audio description information, and sorry, a minute ago I misspoke. I said it's freeform text. There are defined descriptions such as music effects, dialogue, typical things for cinema soundtracks, but you are also able to carry freeform text if you desire. Objects do support sub-elements, and so there's a sub-element count, and we'll look at what those are later. As mentioned, objects are not routed, but they are rendered. And it can reference audio essence carried as PCM or DLC using the audio data ID. As mentioned for cinema, it only supports lossless coding. It supports rendering modifications, mentioned before, spread, which is basically size, snap, zone exclusion, and decorrelation, which we'll discuss in a minute. And the metadata can be updated on a sub-block basis. Sub-blocks are a evenly divided division of a frame, and they depend on the frame rate. For a 24 frame per second bit stream, and for the lower frame rates, typically the duration of the sub-block is about 5 milliseconds. Take a little closer look at these dynamic metadata in the object definition element. Object gain, as you probably could guess, defines the gain for a sub-block. That can, of course, vary over the course of a frame. Object position may or may not change over the course of the frame. This defines position intent. And the reason I call it position intent is, of course, it's up to the renderer and the way the sound system is configured upon playback, how accurately the renderer is going to be able to reproduce the position intended. So that's why a lot of these parameters are defined as intent. Object snap can be thought of, and often is, as the intent to snap the position of an object to the nearest speaker. In the spec, it's defined as the importance of timbre versus position. Basically, if it's set to 1, that means timbre is the highest of the highest importance, and timbre is best preserved from authoring to playback by routing that signal through a single speaker. When you start spreading an object over multiple speakers, you're bound to get some timbre changes. And so it does essentially equate to, if you want to preserve timbre, you snap to the nearest speaker, whereas if you want to preserve position, you use the number of speakers needed to accurately reproduce that. Object zone control. So this is actually used in surround sound today to a certain extent. There are cases where a sound may want to come out of center, but they'll actually use a divergence or a zone, something similar to a zone control that basically says, well, I want this to come from the screen, but I don't want you to use the center channel. And that's basically what this is doing. It allows you to exclude certain speakers from the rendering of a given object. A typical application is a pan that goes from the screen to the back wall through the ceiling, and you may or may not want to include the side wall speakers in that pan, and you can use zone control to exclude side speakers from that, or ceiling speakers if you just want to use wall speakers. Object spread essentially defines the object size. You may or may not want it to be a point source. If you don't want to be a point source, you can give it a size parameter, which can vary from 0, which is a point source, up to 1, which means take up the entire cinema. Object decorrelation. This comes into play if you have an object which has size or is going to be rendered using multiple speakers. Decorrelation sort of mitigates an effect that occurs when the same signal is reproduced over multiple speakers. It can create combing and other effects, and also helps with the impression of size and location. And as mentioned, there's at least one subblock per frame. Well, actually, I haven't mentioned that yet, but I mentioned there could be subblocks. There is always one subblock per frame, and if there are no additional subblocks, then when it comes to rendering, the decoder uses the previous Paninfo block if the current block has none. So that saves a little bit on data. Let's see, before I go into the coordinate system, I thought I'd stop again and see if there are any questions.
In fact, we have a couple questions from our guest, Tom. Tom asks, can you indicate which data items in the standard definition are in use already today, and which ones are put in there for reasons of being future-proof? And then of those that are not used yet, can you explain why they were added to the standard definition? And by in use today, he means content with these data items already being created.
Okay, so I will actually get to that, but I can tell you, a spoiler alert, the elements that I've shown you so far are in current use, and the ones that I'm show you after we review the coordinate systems will be what I would call new. They were added at the request of other participants in the Bitstream Standard Committee. There are other sound systems available, such as Oro, and for instance, the channels and speakers associated with those systems were not represented initially in the spec, and so the channel ID table was amended to include those, as well as the use cases, basically the playback speaker configurations that are supported. And I think that's enough for now. I will, we will get a look at some of these new elements in a minute.
And that is the only question that we have, but I will remind our guests that if you'd like to ask a verbal question and speak directly to Stan, all you need to do is type into the question box, "I have a verbal question," and we'll take those questions anytime throughout the presentation. If you have a text question, type in your question and I will read it on your behalf, and we'll wait until the break when Stan asks for questions.
Okay, great. So I thought, since we just looked at object, it'd be a good time to look at the coordinate systems used for object position. What you see in front of you here is a Cartesian coordinate system with X, Y, and Z axes, with X being basically horizontal, Y being front and back, and Z being vertical. So you can locate any point in this three-dimensional space by a combination of the X, Y, and Z parameters. So that's great if you're talking about the entire universe, but we wanted to constrain that a little bit. So basically for this spec, positional metadata is allocentric, and that means it's based on the cardinal points are based on relative positions relative to certain reference points in the playback environment. And the positional reference is assigned to be the walls of a unit cube. That means the cube has a dimension of 1 on all sides, going from, so all the axes go from 0 to 1, with 0 being one wall and 1 being the other. The origin is defined to be at the intersection of the front wall, which is the screen wall, with the left wall and the height of the base layer. And that's a little hard to see abstractly, so let's take a look at what a reference cube looks like. This shows the front screen wall. The walls have dimensions of 1, and I should point out, even though it looks like this is the cube, it's actually, this is the cube height starts here, because as I mentioned, this is the origin right here, the intersection of the base layer with the left wall and the screen wall at the height of the base layer. And then it shows the various axes, left and right relative to a viewer facing the screen, with a 0 being the left side, 1 being the right wall, and all walls except the floor in this particular location are located at 0 or 1. So here's 0 height, 1 height at the ceiling, 0 horizontal, 1 horizontal, and 0 depth and 1 depth for the back wall. These are all, of course, not really important. That's you could use any set of numbers to use for these reference points, but that's the way it works in this case. So when you see numbers between 0 and 1, it'll give you some idea of where they're located in this ideal cube. And for an example here, the left-hand side here, it shows an idealized location as might show up on a mastering tool. So this represents the authoring environment. This shows the height of the base layer, and basically this green dot locates a point located in XYZ coordinates of 0.25, 0.33, and 0. So X is 0.25, meaning a quarter away from the left wall to the right wall. 0.33 means 33% from the front wall to the back wall, and 0 for height means it's located at the base layer. So in playback in a cinema, now you don't have cubic dimensions, and this plane may actually be slanted, as most typical stadium seating theaters are. But in the relative position, shows the allocentric nature of the rendering system. The relative position is preserved. It's 33% from the front wall to the back, 25% from the left wall to the right, and presented at the base layer. So let's see. And yeah, the point here is that the cinema layout and the dimensions of the cinema affect the precise location, but preserves mapping intent. So the location intent is not intended to indicate that an object is to be produced any specific distance from the screen or any specific distance from the wall, but relative to the front wall and the back wall and relative to the left wall, the location should be preserved. And let's see, yeah, this gets back to the question mentioned a minute ago about the other elements, so I'll be looking at those. This is element which can be a sub-element of a bed, which is called BedRemap. This is included to allow basically remixing of an existing bed. So let's say you've got a bed and you're saying, well, this bed works great for, you know, my standard playback environment. What if it's playback in a different environment that doesn't have all these bed speakers? You can create a down mix or an up mix even that will take the initial bed and remix it. So this structure has the typical elements you're used to seeing of element size and meta ID, excuse me, element ID, size and meta ID. Has a use case, meaning it specifies the use case to use this remap structure in. And in this case, there are source channels and destination channels and remap info per block. So these are actually, this is a source channel count and destination channel count, which creates a loop. So for each destination channel, all of the source channels are applied, a remap gain is applied to each source channel, and there's some to create a output channel, which is the destination channel, and then the destination channel ID tells you where to route it to. So this basically creates a matrix by which you can remix a bed. So this gets back to the question posed a little bit ago. So these are the new elements, meaning these are the elements that are not used in existing Dolby Atmos content. One of them is the object zone definition 19 ID, which is a mouthful. It's called that because it has 19 zones, and it is similar to the object zone control metadata in an object. So it is a sub-element of an object, and it can be used if the renderer recognizes that it's in the environment that supports these 19 zones. And the question was asked, why do we include things like this? And in this case, it was a request from Oro. It is not required for decoders to use unless they support this particular set of zones. There's an authoring tool info element. This is just an informational element, and it allows the Bitstream to carry URI identifying the authoring tool. So if for some applications, the user might want to embed that so the renderer knows what tool created the Bitstream. And then there's a user data element. This was done purely for extensibility purposes. It allows a single ID to be used to identify a user data element, but then there's a user ID, which is a UUID, which is a 16-byte unique number to identify the syntax of the bytes that follow. This is not used in cinema because people felt it would be too open-ended and not backward or not interoperable. Okay, I guess I'll pause again, see if there are any questions. Joel?
We have a few. Next question from Mark is, can the Bitstream be cut frame accurately when editing with video?
Yes, as mentioned, each frame is independently decodable, so you can edit at any frame, and as I'll show in a minute, the MXF file structures that carry the Bitstream do allow locating to any frame in the Bitstream.
Thank you. And Stephen asks, what is the bit rate? Is it constant or does it vary with program material?
Oh, it will definitely vary with program material depending on the number of objects in a given frame. The channels are typically something that stays constant, but due to the nature of the lossless coding, even if all you had were a constant number of channels, the bit rate would vary. But the MXF file structure supports this. I'll point that out a little bit later when I get into that.
Okay. Our guest Sam asks, is it necessary to create all the bed remaps prior to being sent out, or can the renderer be set up at the playout locations to make the adjustments on site?
So this gets into, I guess, customization or adaptation at the playback site. Certainly renderers could take a bed and let's say the renderer says, gee, I don't have all of the speakers that are associated with the bed, and it could have some presets that allow it to downmix the channels in a bed to the set of speakers present on playback. But that is, of course, different than sending metadata to say how to do that. Those would be fixed parameters that would be set in the renderer, and so you just get whatever that renderer did, and render A would do something different than renderer B. Whereas if you do create the remix metadata at the time of authoring and put it in the bitstream, then you would expect similar results for different renders in different environments.
And our final question for this break comes from Paul. Paul asks, is the frame rate per bit stream, i.e. if you wanted to use the IAB with 23.98 and 29.97 video, would you need 2 bit streams?
Well, the bitstream is frame based, so yes, if you basically have to create frames when you create the bitstream, and you have to select a frame rate. So if you have a target in video rate, which is 1 rate, you need to create your bitstream for that. Now, of course, there are master files that exist before the bitstream is created, and the master file can consist of a bunch of WAV files and a bunch of blobs of metadata that are then parceled into frames. But so that master could remain the same, but in terms of once it's put into a bitstream, it does need to be set to a fixed frame rate.
Thank you, Stan. That's all the questions we have for the moment.
All right. So let's see. We'll talk a little bit now about backward compatibility. So as mentioned, many elements in this bitstream were based on an existing practice, which is Dolby Atmos. That was the basis for this. So in order to, the goal of this bitstream standard was that existing bitstreams would be compliant with the standard, such that there would be nothing put in the standard that would make existing bitstreams non-compliant with it. So that put some constraints that we couldn't put any new required elements in, and no changes to syntax for existing elements. Although, as I mentioned, some new codes were added for more channels and more use cases. And then, as mentioned, decoders can skip unrecognized elements, so that does allow new elements to be added. But the result is that existing bitstreams are compliant, but new bitstreams may or may not work properly with existing decoders, depending on the use of these new elements. Okay, so let's take a look at element hierarchy. This gets back to the logical view of the bitstream. This is basically a UML diagram for those of you that are familiar with that, which shows how certain objects are composed of other data objects. This shows that the high A-frame is the highest level in that it contains all the other possible elements. you'll notice this number here, 0, means that that is the number of elements of this type that are required in a frame. And you notice they're all 0. So there are no required elements in the bitstream according to the spec. You'll also notice some elements have can be composed of other elements. And in fact, the bed definition can be composed of 2 types of sub-elements. It can be composed of another bed definition element, and it can be composed of can contain a BedRemap element. And again, those are both 0 or more. An object can contain another object, and it contain an object zone definition element, which as mentioned can replace the object control information. The other elements do not support any sub-elements, as noted here. And in summary, this shows what the IAFrames are composed of. It shows that all elements are optional. It shows that some, not all elements can contain sub-elements. And especially when we get talking about conditional elements, it's important to note the parent-child relationship. So any element that's contained in another element is considered a child of that element. So basically, all these elements are children of an IAFrame, which is the highest level. And any element which is contained in another element is considered the child of that element. And this will get important when we talk about how conditional elements work. And as we'll see later, a child will replace all or a portion of a parent if used. So now we're set up to talk about conditional bitstream elements. Basically, the reason for conditional bitstream elements, they're not always rendered. They're rendered if the use case is met. It allows a bitstream creator to supplement the bitstream for alternate target environments. I think I mentioned this earlier. You've got this nice bitstream created, and it's set up assuming certain speaker configuration on playback. There's a bed set up for it. There's objects set up for it. But what if it's playback in a different environment? You might want to send additional metadata to tailor how the bitstream is rendered in those environments. If there is a conditional element, it'll always be associated with a use case code. A use case code represents a specific playback condition, also known as a target environment. Basically a set of speakers. Conditional element can be a child or a top-level element. If you refer back to that diagram I mentioned a minute ago, there's some beds. There's a bed and object that report directly to the frame. Those are considered top-level elements. Even those top-level elements can be conditional. And as mentioned earlier, a conditional child element replaces a parent or a part of it if it's used. And basically, the renderer is what determines determines the use case that it is set up for based on the speaker configuration. So this is a one-time setup. Renderer is put in an environment. The person setting up the renderer tells the renderer the location and number of speakers and whether they're arrays or individually addressable. And now the renderer knows about the playback environment and can set a use case code that it reports to the decoder that determines which elements then are used during rendering. And based on that, then it's only rendered, the conditional elements are only rendered if the renderer configuration matches the use case associated with that bitstream element. So what are the conditional bitstream elements? You can have a conditional bed. As mentioned, this replaces a parent bed with a new mix. So there's new audio essence actually associated with this. So this isn't just a remixing, it's actually new channels sent, perhaps a different number of channels. Again, if the use case is met, then this bed is used instead of the parent. You could have a conditional object. Let's say you're concerned about how an object is rendered in a specific environment. You might say, gee, if it's going to be rendered in this type of environment, I don't want that object to be there. I want it to be here. So you can send a conditional object that's used in that use case. And in this case, it may or may not use new audio essence. You may keep the essence the same. Let's say it's a car horn or something like that. You don't want to change that, but you just want to change its location. So in that case, you send new metadata. But of course, the object does have an audio data ID, so it can point to new essence if you prefer. The bed remap we've looked at, that is always a conditional element, and it remixes the parent bed channels to create an alternate mix. In this case, there is no new essence, it just remixes the essence that's in the parent bed. Let's see, maybe it's a good time to, since this is a complex topic, maybe we could stop here, Joel, and see, are there any questions on conditional elements?
Well, we have a question from Joseph, and the question is, the Bitstream frames are not at the same rate as the picture frames, correct?
No, they are intended to be. When you set the frame rate of the Bitstream, the idea is you're creating audio to go with a video presentation, so you would choose a frame rate which matches picture.
Great, thank you. And Dan asks, will the slides be available after the webinar? And I think I may have forgotten to mention this at the beginning, but I invite our guests to stay with us until the very end of the webcast. And towards the end of the webcast, I will be placing a link in the chat box to the online feedback form. And once you submit the completed online feedback form, which is very important to us to making sure that we continue to do things that are relevant and that we continue to do the things that work and to stop the things that don't work. But I'll be putting that link in the chat box towards the end of the session, and once you submit it, you'll be automatically redirected to a PDF of the slides that Stan is presenting today. And that is all the questions we have for now.
Okay, good. So now I would like to present some examples to show how this all comes together in typical uses and to associate some actual numbers so you see how this all works. These are simplified objects showing an element. The element name is at the top, and a subset of the parameters inside the element are illustrated along with the values that they'd be set to in this example to show how it's used. This line, vertical line, indicates that this element is contained in the element above, so that shows the child-parent relationship. So with that explanation, let's start at the top with the immersive audio frame. The element ID has been set to 8 because the specification defines that that is the element ID associated with an immersive audio frame. The version has been set to 1. That is the value defined in the spec to be associated with this particular Bitstream spec. Max rendered is a number which indicates to the renderer how many audio elements it's going to have to deal with, and this is a combination of the number of channels and objects that the maximum number of channels and objects that might be rendered at any given time within that frame, and we'll see how that works in a minute. Sub-element count was mentioned earlier. This is how the parser knows how many elements, sub-elements it has to deal with. In this case, it's set to 1. You might say, well, gee, aren't there 2 sub-elements here because there's a bed definition and a bed remap? But in this case, the sub-element count is set by the top-level element. Since the bed remap is actually contained in the bed definition element, the IAFrame only has 1 sub-element. Then you move to that sub-element and you find, oh, there's another sub-element there. but that's the way sub-element count is set. So moving on to bed definition, it has unique element IDs, in this case 10, a unique meta ID set to 1, conditional bed is set to 0. So in this case, the bed itself is not conditional, so it doesn't depend on the use case whether the bed is used or not. It has a sub-element count of 1 that indicates that's due to this BedRemap sub-element, which has an element ID of 2, meta ID of 1. Again, I'd like to point out that meta ID does not have to be unique within a frame. It only has the combination of element ID and meta ID have to be unique. So basically, meta ID allows you to identify which element of any given element type is within a frame. It allows you to distinguish between different elements that may have the same ID. This remap use case has been set to 1. I happen to know that means a 5.1 playback environment, even though that's not immersive. It's a simple thing. It is included in the spec, and it's simple to include for this example. And note that the source channels, which is based on the parent bed, is set to 10 because the channel count in the parent is 10. The destination channels is 6 because that's how many channels there are in 5.1. Going back to max rendered, this was set based on looking at the channel count in both of these sub-elements and saying, well, this one renders 10, this one renders 6, looks like max is 10. So to summarize, as I mentioned, this diagram shows the relationships. The remap use case is 1, which indicates 5.1. I've mentioned the source and channel count, or destination channel count. And to reiterate, the bed remap is used if and only if the render configuration indicates a 5.1 playback environment. All right, there's another example. I guess I call this more typical in that there's a bed and an object involved. I should point out that active elements are rendered simultaneously. So in this case, neither of these elements is conditional. The bed is not conditional. The object is not conditional. So that tells the renderer, well, these are both active. They're going to be summed. And this works. You can actually have multiple beds reporting to a single frame. There's no constraint on that. And as mentioned, max rendered is the total of bed channels plus objects. So again, getting into the details of what's in each frame in the example, it's got the element ID to indicate it's a frame. The version ID is 1. The max rendered is 11. We'll figure out how that was derived in a minute. Sub-element count is 2. There are 2 separate elements here that are not, neither one is a child of the other, so the sub-element count is 2. Bed definition has an element ID of 10, a unique meta ID of 1. It's not conditional. Channel count is 10, and sub-element count is 0. Object has an element ID of 40, meta ID of 2, just to be different. It's not conditional and no sub-elements. So if you count the number of channels plus the single object, max rendered is set to 11 in this example. And I think this is the final example. This shows how conditional beds work. In this example, you've got the IAFrame composed of a top-level bed definition element that has 2 sub-elements that are both bed definition elements. And they have different use cases. This is actually a constraint of the Bitstream that's not a constraint. I'll get into that in a minute. These could actually have be played at the same time, but we do have constraints on the number and types of sub-elements to keep things from getting out of hand. As mentioned, the child beds replace the parent under a specific use case. So the use case for this one is 1, which is 5.1. In this case, it's 2, which is 7.1. So they will each get used under their specific use cases, and if that use case doesn't exist, neither will get used. As mentioned, a conditional bed carries additional essence, so it's a complete remix. And as I alluded to, the Bitstream standard does constrain the number of child elements. It does not allow children of children. So, for instance, you can't have a child bed definition element under this bed. You couldn't have a child under this bed. You could have any number of child beds at this level. And just to keep the renderers from having to be over-designed, max rendered is set, cannot exceed 128, and that number is actually dependent on the bit rate set for the audio, the audio sample rate set. So it could be 128 if the audio sample rate is 48 kilohertz, or 64 if the audio sample rate is 96 kilohertz. And I think that's all the examples, so I guess I'll stop at this point and ask if there are any questions.
There are no questions at this time.
Okay, very good. Well, we're getting to the home stretch here. I wanted to take a minute to talk about some of the coding efficiency that's built into the Bitstream. So metadata in essence is only present in a frame if needed in that frame. In particular, objects need not persist if they're not used. Let's say you've got a, you're using a particular object ID in a scene, and the next scene or the rest of the movie, that object's not present. You would not include the object or the essence in any of the subsequent frames. You could also use that ID for a completely different object, a different sound, in a different portion of the program. But the point here is that you only include metadata and essence for objects, at least when they're needed. Channels are a little different since they are intended to exist for the entire length of the program, but I'll get into how that is done efficiently in a minute. The clicker doesn't seem to be working, and I don't want to get too far ahead. There we go. As mentioned, subblocks, which of course there are different, yeah, too many there. Subblocks are only used to carry metadata that changes over a frame. So if the metadata doesn't change over a frame, you don't include more than one subblock in that frame, and only objects and remix elements even support subblocks. And audio essence can be losslessly coded in a cinema. That is the requirement. That typically saves you 2-to-1 on audio over the course of a program. Depending on the type of audio, that can go way up like to 10-to-1 or more, or down to 1-to-1 for something like pink noise. And there is an additional savings in each frame if the source audio going into the encoder is actually silent for the duration of that frame for that particular audio essence element. You can code that by referring to an audio data ID of 0. And this basically then is just carried as metadata and instructs the decoder to reproduce audio silence for that audio essence element for that frame, and that can result in quite a bit of savings. Anecdotally, I can report, having worked with Dolby Atmos for several years, we can see the existing, what's called a main audio track, which carries typically 14 channels of PCM audio. And of course, that track, if it carries silence, that actually has to be coded in. And you compare the 14-channel main audio track to the size of the immersive audio track file, and they're often comparable in size. Sometimes the immersive audio is larger, sometimes smaller, but it's not a big difference. And speaking of cinema, I wanted to talk about the applications. The Bitstream is not intended to be used by itself. It needs to be carried in a file for delivery. And of course, SMPTE is working on standards for doing that. Again, there was a preference expressed by a lot of the proponents of this work that the existing files be used as much as possible. So the actual track files used to deliver Atmos are basically in the process of being standardized through SMPTE, so that existing equipment that's used to creating those and playing those back can continue to work. So this is again a structural look at how the file is created, just to give you an idea of how the Bitstream gets packaged. In the case of cinema, the Bitstream is what's called frame wrapped. That means each individual Bitstream frame is wrapped in a KLV structure. The key indicates that the payload of that KLV packet is a Bitstream frame according to ST 2098-2. So you know exactly what is carried. And then these frames are concatenated and combined with a header and a footer to create a ST 429-18 immersive audio track file. As noted at the top of this slide, this is a work that is in progress. The intent that it will be compatible with what's out in the field today is going to hold, but the actual SMPTE standard is still in the drafting group stage, but we hope to get those to ballot and published soon. I should also mention ST 429-18 not only defines what goes in an immersive audio track file, the composition playlist also needs to have a new asset type defined to support immersive audio essence. So it handles that and also handles some constraints that need to be applied to the Bitstream in order to be put into an immersive audio track file. Let me see, let me go back. I wanted to mention one other thing. This footer, it was mentioned earlier, asked earlier, can you access the content once it's wrapped frame by frame? The footer in an MXF file carries an index table. So even though these frames are different size, when this file is created, it basically puts the size of every frame into this index table. So it allows you to say, if you want to go to frame 156, you look in the index table, it'll tell you how to get there, how many bytes to skip to get there. So the cinema was the first application, but right on the heels of that, there was interest from the studio community and others to put immersive audio in IMF. That's a popular application. It stands for interoperable master format. Allows the interchange of master quality files for distribution to secondary encoding processes that would typically encode them for emissions to the home via OTT or DVD, things like that. So that is also in progress. Again, we start with the Bitstream frames as defined by 2098-2. And I should mention that at the start of the IMF application process, it was noted that the Bitstream did not support some important frame rates that were needed by the proponents. So additional frame rates were added to the spec, additional channels were added to the spec. And so this shows how the Bitstream is somewhat future extensible. And then in terms of cinema applications, we're able to constrain those to not have to support the IMF amendments, so there will be a single standard going forward. In the case of IMF, audio is defined to be clip wrapped, meaning all all of the essence is put in a single KLB structure. So in this case, there's an MXF clip with the key saying that this is an IAB bit stream that is clip wrapped. Waiting, see if that click worked. Here it comes. There it is. The standard is ST2067-201. As mentioned, that is in progress. That's actually, if you're familiar with the SMPTE process, that has started FCD ballot, which is one of 2 ballots that takes place before it goes into the publication queue. So this is fairly far along. The mechanism for adding new essence types to IMF is called a plugin. So this is called an Immersive Audio Bitstream IMF Level 0 plugin. So the document contains all of the supplemental information that is needed to define what needs to be done to the base IMF specs to support this new essence type. So it defines one of the fundamental things it defines is what we're looking at here, which is going to be called an IAB track file. And that is also pointed to by a playlist, in this case an MXF playlist. So the 2067-201 spec identifies how that is done. And this shows the file structure, which is a header, a footer, the clip is mentioned up here. I'll also mention a couple other things. The spec allows for the inclusion of a additional generic stream partition to carry additional program level metadata. This metadata is defined in the spec to not be germane to the rendering of the individual frames, but could carry additional information that might be useful for encoding or identifying the program, things like that. The footer, as before, carries a index table. And let's see, yeah. So in this case, again, the index table is created at the time the MXF clip is created, and it keeps track of how many bytes are used by each edit unit, which is an MXF term for the units that you might want to access when you edit this. So using this file, you are still able to access any frame in the file. And so, it's been a little bit faster than I thought. So we're pretty much at the conclusion here. And to summarize, ST2098-2 is an efficient, flexible, extensible standard that supports the features needed to convey immersive audio essence and rendering intent. It's backward compatible with existing immersive audio content, i.e. Dolby Atmos. And file transport will soon be supported, file transfer of the bitstream will soon be supported by SMPTE standards for D-Cinema packaging and IMF. And we hope this will really facilitate the interchange of immersive audio in lots of new applications and facilitate existing ones and make things easier for everybody. And with that, I guess we'll open it up to more questions.
Thank you very much. Let's see, we have a couple in the queue, but we invite our guests who are still with us. We still have 79 people, which is good. We invite you to submit your questions either in writing, in text, or orally. And of course, the oral questions take precedence and will go right to the top of the list regardless of how many questions there are in the queue. And as I mentioned previously, I will be placing a link in the chat shortly so that you can go and provide us with your feedback. Once you submit that completed feedback form, you will be automatically redirected to a PDF of slides that Stan presented today. Stan, let's see, Mel asked the question, how will the emergent SMPTE standard affect the data files that a re-recording stage delivers to the film studio? Will there be transform utility to convert, for example, a Dolby Atmos immersive mix to SMPTE 25 CSS and hence to the DLP?
Well, as mentioned, a goal of the standard was that existing Dolby Atmos bit streams would be compliant with the spec. So if you are currently producing Dolby Atmos bit streams and the track files that carry them, you will be compliant with the standard. In terms of some of these other formats, I don't know about conversion tools. Certainly, in terms of I can tell you there are other companies that do intend to make authoring tools and are working on those now. And there's going to be a plug fest sponsored by the ISDCF for the various companies that produce that want to produce bit streams and immersive audio track files, to get together and exchange those and try to play them back and make sure that people are interpreting the standard correctly and that everything interchanges.
Great. Let's see. Mark is back with another question. Thank you for asking questions, Mark. He asks, how would you gauge the current interest or plans to adopt the standard as an authoring medium by post-production vendors and manufacturers?
I'm sorry, I'm not sure I got all that. Can you repeat that, please?
Sure. How would you gauge the current interest or plans to adopt the standard as an authoring medium by post-production vendors and manufacturers? Do you have any sense?
Yeah, so, well, certainly there was a lot of interest from makers of those types of tools and users during the development of this standard. So we do expect it to see, certainly within cinema, we do expect this to become the standard, and hopefully also in IMF for immersive audio. Some of you may or may not be familiar with a lot of cinema packaging is based on a open source tool set maintained by Cinecert called ASDCP-lib. So that will support this standard for D-Cinema and also for IMF packaging eventually. So the tools for creating the files will certainly be available. Authoring of the bitstream will depend on various companies and their business interests, but certainly Dolby will continue to make authoring tools available, and I'm aware of at least one other company that is planning to do so as well.
Thank you. Next question is from Sean. On the studio side, is there an audio mastering difference between the DCP cinema release and the IMF home release?
My understanding is yes. There doesn't have to be. In other words, you could take a cinema, well, sorry, I take that back. You could not take a cinema bitstream and send it to IMF because the IMF standard will not support the lossless coding. Since it's a master format, even though it's lossless coding, we decided to stick with PCM. That was partly because some of the fractional frame rates were requested to be supported. It was a lot easier to support those with PCM than with lossless coding. But that's not really a question about limitations or features of the bit stream. It certainly it supports either. Typically what happens though, my understanding is because we're talking about a near field environment in the home, typically they'll take a mix and a cinema mix and remix it using near field speakers for the home with a home immersive system. So it is different mix, and it has to be different by virtue of the slightly different technical specs between the two.
Okay, great. Thank you. And that is all the questions that we have for right now. I have placed the link to the online feedback form, and that will lead you to the PDF of slides once you submit the completed form. Stan, I'd like to thank you for an interesting presentation, and I'd like to thank our guests for joining us today, and hope to see everybody on a future SMPTE webcast, whether it be in the Standards Update series or in our technology series. So with that, Everybody, I hope you have a good day. Take care. If you're traveling, safe travels, and we'll see you next time.